Even though the frontier-based exploration is, let's say, quite working, we have additional techniques that may provide some more theoretical grounded approaches, and it is related to information theory employed in exploration scenarios. So one of the drawbacks is that in a frontier-based exploration, we assume perfect knowledge about the robot states, and also the utility function depends only on the map. And we can avoid such assumption by defining a control policy as a rule how to select the robot action that reduce the uncertainty of estimate by learning measurements. So we basically formulate the problem in this very informative path planning based approach. So we have a set of possible actions, and we are looking for the best action that will increase our information. So we have the future estimate, we have the future measurement, and we have the action. So we and here it is the mutual information, and it expresses how much uncertainty of X will be reduced by learning Z. This is the new measurement. So for the mutual information, you can compute using this entropy and conditional or predicted entropy. And the conditional entropy is expected uncertainty of X after learning Z. So collecting new measurements. For example, the entropy can be computed using the known probability density functions. So what we can do is that in this exploration or grid-based exploration, we can have the sensor placement approach with raycasting of the sensor beam and determination of distribution over the range returns. And you can probably sense that precise computing of mutual information is computationally very demanding, and it may not be feasible for a large set of actions and uncertainty of action results. But we can a little bit simplify that, and we can assume that the observation removes all uncertainty from observed areas, which actually simplifies the problem a lot, because we get rid of this conditional entropy. So we will have something like this, and in this case we can decrease the computational requirements significantly because we can just compute the entropy of the sense regions in the current map. So what we are doing, we are maximizing the mutual information in the sensor placement problem of observing the region with the maximum entropy. So if we have our next action, so we just, for example, move from this location to that location, and during this movement, that can be the path, we can actually sense some areas surround, and that's defined this region of action A. So this is the action A, this is the region of action A. So we compute the maximum entropy. We compute the sum of the entropy, and we compute the action that will maximize this entropy. So that simplifies a lot. And there is also the another approach that instead of mutual information, we can compute Cauchy-Schwarz quadratic mutual information, which has the similar notion, but it is easier to compute. And again, take a look to this reference if you are more interested. So how it is actually working, just few images. So we have these clusters. Again, we can consider the frontiers, and we like to determine what will be the benefit or the information we will collect. So we can sample some processes to cover a particular cluster, and we can do that for each of the cluster of frontiers. So we plan a path to some sampled processes of this. So for example, some of these. And then we select the action that maximize the rate of this mutual information or Cauchy-Schwarz quadratic mutual information. But you can also consider other simplifications. So wow, it is from the 3D perspective. So you have this robot, so we can move. As we move, so we capture that. We move a little bit, we capture that, and so on. And you can imagine that this is quite demanding. Of course, it is still demanding, but as you can see in these videos, it can be deployed on real robots. Of course, there is for UAV it's a little bit faster, but it's still quite speed up. And for the ground robots again, but it is working, and it has been demonstrated that such approach can be deployed on the robots. So if you are more interested in Ben Charo's work, take a look to the paper at RSS 2015. And if you remember that we mentioned some example of the kriging using the Gaussian processes of drawing spatial phenomena, we can also consider kriging in this information theoretic based approaches. And so the nice idea or a nice feature of Gaussian processes or Gaussian process regressors is this uncertainty representation, because you have these estimates on the confidence or variance of the model. And we can consider differential entropy of normal distribution, and it's a function of the variance. And we can employ the greedy approach to actually sample the highest prediction, the location with the highest prediction variance in very, very similar way. And one of the example is a little bit, let's say, a generalized exploration, where we are not building only the model of the environment, but also building communication maps, as Alberto did in his very recent paper. So we have a pairwise problem. So we need to select location of two robots to sample the communication signal strength. But basically, it is just another, let's say, just another optimization function, and we need to elaborate on the possible ways. But it's the whole notion that we are diminishing the variance is the same. So again, if you are interested, take a look to the provided reference. So what you can actually deal with in these kriging scenarios, especially in a combination of the exploration and some sort of search, because you are building the spatial model because you don't know about the environment. And on top of that, you build your phenomena model, for example, using the Gaussian process. And you are actually search for something. You are searching for diminishing the uncertainty or source of radiation heat or some other functions extreme. And in that case, you actually need to balance the exploitation and exploration. So it's the very known dilemma. And you can exploit your model to actually find the source of radiation, for example, or explore the environment to actually collect information about the unseen part. One of the approaches, Gaussian process upper confidence bound, which addresses the search process as a multi-armed bandit problem. So if you remember your courses on AI, so this is one of the application in robotics. So the policy is actually choosing the next sample point according to argument maxima that we have this exploitation part and the exploration part, and we have some scaling or ratio factor to that. And there are a couple of approaches. Andreas Krauss is one of the sampling design researcher. It's also worth of taking a look to his publication record if you're interested in this field. And a relatively recent adaptive sampling on online learning in multi-robot sensor coverage with mixture Gaussian processes. So in this case, we have a team of robots that aims to discover the underlying phenomena using Gaussian processes notion. So to complete our tour of exploration and exploration with uncertainty or sources of uncertainty, we should not forget that the reliable localization is the fundamental piece to have a precise map of the environment. So, and you can probably already acquire the experience that in environment that you visit first, you completely rely on your SLAM, on your simultaneous localization mapping technique, unless you have a viable GPS, precise GPS. So if you return to your previously visited area, you can improve, you can support the localization like this ICP algorithm and provide a better localization. But you like to visit the unseen parts because you are exploring. So you can put these uncertainties together or mutual information. So you can have the occupancy. That's for the model of the spatial environment, and you can have the localization uncertainty. So you can express that as also using the entropy, where P is the covariance of location of the robot, and localization of landmarks if you have the landmarks that you are using for the localization. But here we have the Shannon's entropy of the map and differential entropy of these processes. So that's troublesome from the computational point of view. So that's the problem we need to address. And of course, there are a couple of approaches. And but what we can actually consider that the exploring unit may strictly prefer to improve either its map or localization. So we have this, so we can adjust by this gamma. And how we can actually address that in some let's say convenient or elegant way. It is the notion of René's entropy, which can be considered as a generalization of the Shannon entropy, because for the special case of this alpha equal 1, we will have Shannon entropy. So then the utility function is taking action A as a difference of the Shannon entropy and this René's entropy. So the Shannon entropy is for the map, and the René's entropy is for the localization. Where we have this as a predictive position uncertainty to a given action. And that's the question, if we have a robot that moves somewhere, how we can predict the position. But again, this is out of the scope of this lecture and also the course. But if you're interested, this is the one of the starting point. You can start your survey or research. At the very end, let me talk about exploration and search, and because I like that you will acquire that there are a few differences, because in exploration we usually aim to create a map, but in a search scenario, we are searching for objects, and to assure that we search the whole environment, we may need the map. But the purpose is different. It's similar to the SLAM. So here we can use the map to support the robots to make a decision and to ensure that we search the whole environment. But the primary purpose is to search the object, like this backpack, and report the backpack position as quickly as possible and as precisely as possible. So what you can see here is an example of the performance of the CTU Krasnor lab team during the DARPA Subterranean Challenge and Urban Circuit. So here the robots are requested to fully autonomously, once they are entered to the site, explore and search the environment, and to find the artifacts and report these artifacts and report what is type of the artifact and report the position in less than 5 meters. So in this urban scenario, the robots starts at a single platform, but also need to pass the stairs or can use the drones to explore some upper levels of the environment. And hopefully find some of the artifacts. In this particular case, there was one of the artifacts was also the detection of CO2, a gas, in some particular rooms, and in addition to the backpack, cell phones, and so on. So this is one of the tracked robot traversing the stairs and finding and scoring for the backpack. So you can imagine that this is a very complex robotic system where particular parts of this also exploration and information gathering is employed, in addition to the robust localization and navigation. And in this case, everything has to be done during the mission. So you cannot pre-plan much of that. So, and you can collect this map, but the map is not the results, not the result for the search mission. So the goal, the objective is to report the artifacts. So let me summarize the lecture. You should acquire some notion about robotic information gathering that can be formulated as an informative path planning. And we spent some few slides on robotic exploration, where you become familiar with the occupancy grid, basically frontier-based exploration, and relations to the decision-making parts, and how it is affecting the performance of the exploration. I provide you the TSP distance cost. It can improve the frontier-based exploration together with the clustering and free edges and representative of these free edges. So we will not consider all these frontier cells, but just one single representative like this one. I also provide you multi-robot exploration as a task allocation. I would like to motivate you to use maybe Hungarian algorithm, MTSP, or the MinPos because of your semester project. And if you are also interested in this information theoretic approaches with mutual information, I also suggest for the semester project to score more points, to consider one of these, and ask the teachers during the labs how to approach and how to select the let's say at particular implementation cost efficient approach. We will continue on robotic information gathering and relation to the multi-goal planning in the next